According to Section 430.52 of the 2002 National Electrical Code, the overcurrent protection for a three-phase motor with a full load amperage of 52 amps can be rated up to 250% of the full load amperage. Therefore, a 130 amp circuit breaker calculated as 52 amps times 250% would be acceptable. However, it is important to note that the engineer is correct in pointing out that a 200 amp circuit breaker does not provide adequate protection for number 4 American wire gauge conductors. Table 310.15 B16 of the 2002 National Electrical Code specifies the ampacity of number 4 American wire gauge copper conductors as 85 amps. To address this situation, you have two options. Firstly, you can replace the 200 amp circuit breaker with a 130 amp circuit breaker. Secondly, you can install a separate overcurrent protection device specifically for the conductors, such as a fuse or a thermal overload relay. It seems there was a misunderstanding of Section 430.52 of the 2002 National Electrical Code. While this section allows for a circuit breaker rated up to 250% of the full load amperage, it does not exempt the circuit breaker from the fundamental requirement of providing adequate protection for the conductors themselves. The engineer is correct in insisting that the conductors be adequately protected. To rectify the situation, the options are either replacing the existing 200 amp circuit breaker with the 130 amp circuit breaker or installing a separate overcurrent protection device dedicated to safeguarding the conductors. Now let's delve deeper into the specifics of motor overcurrent protection and conductor sizing according to the National Electrical Code. Understanding these requirements is crucial for ensuring electrical safety and code compliance in motor installations. Section 430 of the National Electrical Code provides comprehensive guidelines for the protection of motors, motor circuits, and motor control apparatus. These guidelines are designed to prevent damage to equipment and hazards to personnel that can arise from overloads, short circuits, and ground faults. When selecting overcurrent protection for a motor, it's essential to consider both the motor's full load amperage and the ampacity of the conductors supplying the motor. The motor's full load amperage is the current the motor draws when operating at its rated horsepower and voltage. This information is typically found on the motor's nameplate. The ampacity of a conductor is its current carrying capacity, which is the maximum amount of current the conductor can safely carry without overheating. Conductor ampacity is determined by factors such as the conductor's size, material, insulation type, and ambient temperature. Table 310.15 B16 of the National Electrical Code provides ampacity ratings for various types of conductors based on these factors. In the situation described, the motor has a full load amperage of 52 amps and is supplied by number 4 American wire gauge copper conductors. According to Table 310.15 B16, number 4 American wire gauge copper conductors with typical insulation types such as THHN or THWN have an ampacity of 85 amps when installed in raceway cable. This means that the conductors are capable of safely carrying 85 amps of current. Section 430.52 of the National Electrical Code allows for the use of an overcurrent protective device, such as a circuit breaker or fuse, rated up to 250% of the motor's full load amperage. This allowance is intended to accommodate the motor's inrush current, which is the high current that the motor draws when it is first started. The inrush current can be several times higher than the motor's full load amperage, and a standard overcurrent protective device size to protect the conductors would likely trip during motor starting. However, it's crucial to understand that this allowance does not exempt the overcurrent protective device from the requirement of protecting the conductors. The overcurrent protective device must still be sized to protect the conductors from overcurrents caused by short circuits or ground faults. In the situation described, a 200 amp circuit breaker is installed to protect the motor circuit. While this circuit breaker is within the allowable range of 250% of the motor's full load amperage, it exceeds the ampacity of the number 4 American wire gauge conductors. This means that if a short circuit or ground fault were to occur, the conductors could overheat and potentially cause a fire before the 200 amp circuit breaker trips. Therefore, the 200 amp circuit breaker does not provide adequate protection for the conductors. To correct this situation, there are two options. Firstly, the 200 amp circuit breaker can be replaced with a 130 amp circuit breaker. This size is calculated by taking 250% of the FLA 52 amps. This circuit breaker will provide adequate protection for the conductors while still allowing the motor to start without tripping the breaker due to inrush current. Secondly, a separate overcurrent protection device can be installed specifically to protect the conductors. This device could be a fuse or a thermal overload relay. The fuse or thermal overload relay should be sized to protect the conductors at their ampacity rating of 85 amps. This would provide an additional layer of protection for the conductors in the event of a short circuit or ground fault. In addition to the overcurrent protection requirements, Section 430 of the National Electrical Code also includes requirements for motor overload protection. Overload protection is designed to protect the motor from damage caused by prolonged overcurrents that are less than short circuit or ground fault currents. These overcurrents can be caused by factors such as excessive load on the motor, low voltage, or a locked rotor. Motor overload protection is typically provided by thermal overload relays or electronic motor protection relays. These devices sense the motor's current and trip the circuit if the current exceeds a preset level for a certain period of time. The overload protection device should be sized to protect the motor from damage without causing nuisance tripping during normal operation. In summary, when installing a motor, it is essential to select overcurrent and overload protection devices that are properly sized to protect both the motor and the conductors. The overcurrent protection device should be sized to protect the conductors from short circuits and ground faults, while the overload protection device should be sized to protect the motor from damage caused by prolonged overcurrents. By following the requirements of Section 430 of the National Electrical Code, you can ensure that motor installations are safe and code compliant. Let's reiterate the key points for clarity. Firstly, always refer to the motor's nameplate for the full load amperage and other important information. Secondly, consult Table 310.15. B16 of the National Electrical Code to determine the ampacity of the conductors based on their size, material, insulation type, and installation method. Thirdly, select an overcurrent protective device that is sized to protect both the motor and the conductors. Fourthly, ensure that the motor is provided with adequate overload protection. Finally, always follow all applicable codes and standards when installing motors and motor circuits. By adhering to these guidelines, electricians and engineers can ensure safe and reliable motor installations. Now, let's consider some additional factors that may influence the selection of overcurrent protection for motors. Firstly, the type of motor can affect the allowable overcurrent protection rating. For example, motors with high inrush currents, such as those used in some HVAC applications, may require higher overcurrent protection ratings than motors with lower inrush currents. Secondly, the application of the motor can also affect the overcurrent protection requirements. For example, motors that are used in critical applications, such as fire pumps or emergency generators, may require more stringent overcurrent protection than motors that are used in non-critical applications. Thirdly, the ambient temperature can also affect the ampacity of conductors. If the ambient temperature is high, the ampacity of the conductors may need to be deaerated to prevent overheating. Deaerating factors are provided in Table 310.15. B2 of the National Electrical Code. Fourthly, the presence of harmonics in the electrical system can also affect the selection of overcurrent protection. Harmonics can cause the conductors to overheat, and it may be necessary to use conductors with a higher ampacity rating or to install harmonic filters to mitigate the effects of harmonics. When selecting overcurrent protection for motors, it is also important to consider the interrupting rating of the overcurrent protective device. The interrupting rating is the maximum amount of fault current that the device can safely interrupt without being damaged. The interrupting rating of the overcurrent protective device must be greater than the available fault current at the point of installation. The available fault current can be determined by performing a fault current study. Finally, it is essential to ensure that all overcurrent protection devices are properly labeled and identified. The label should clearly indicate the device's ampere rating, interrupting rating, and other relevant information. This will help to ensure that the devices are properly maintained and that they are not replaced with incorrect devices. In conclusion, selecting the appropriate overcurrent protection for motors requires a thorough understanding of the National Electrical Code, motor characteristics, conductor ampacity, and other relevant factors. By carefully considering these factors, electricians and engineers can ensure safe, reliable, and code-compliant motor installations. Remember that this information is based on the 2002 National Electrical Code. Subsequent editions of the National Electrical Code may have different requirements. Always refer to the latest edition of the National Electrical Code for the most up-to-date information. It is also recommended to consult with a qualified electrical engineer or inspector if you have any questions or concerns about motor overcurrent protection. They can provide expert guidance and ensure that your motor installations comply with all applicable codes and standards. Furthermore, specific local amendments or regulations might supersede or add to the National Electrical Code provisions. Always check with local authorities having jurisdiction, often referred to as the HJ, to verify compliance with all applicable rules. Ignoring local requirements could lead to failed inspections and potential safety hazards. Proper documentation is also crucial. Maintain accurate records of all calculations, equipment specifications, and installation details. This documentation will be valuable for future maintenance, troubleshooting, and inspections. Consider using a checklist to ensure that all necessary steps are completed during the motor installation process. This checklist should include items such as verifying conductor ampacity, selecting appropriate overcurrent protection, and testing the motor for proper operation. Regular inspections and maintenance are essential for ensuring the continued safe and reliable operation of motor installations. Inspections should include checking for loose connections, damaged insulation, and other signs of wear or damage. Maintenance should include cleaning the motor, lubricating bearings, and testing the overcurrent and overload protection devices. By following these best practices, you can minimize the risk of electrical hazards and ensure the long-term performance of your motor installations. Remember, electrical safety is paramount. Always de-energize circuits before working on them, and use appropriate personal protective equipment, such as gloves and safety glasses. If you are not qualified to perform electrical work, hire a licensed electrician. Learning the intricacies of electrical codes and practices is a continuous process. Attend training courses, read industry publications, and stay up to date on the latest changes in the National Electrical Code and other relevant standards. By investing in your knowledge and skills, you can become a more competent and confident electrical professional.